Well, now that we have a good grounding in rotational kinematics, the description of rotation, it's time to endeavor into the realms of dynamics, the cause of rotational motion. So this will bring us into vistas of new problem-solving skills and revelations that we need to embrace with our hearts and our souls, assuming we have those. And we start with the cause of motion, not just any motion, rotational motion, and that is torque. So simplistically, it could be thought of as a twisting force, but we'll define it better than that. I like to use the symbol cap gamma, which is not the traditional symbol, but because when I write things, you can't tell the difference between one symbol and another when I write it. This just kind of has the functional dimensions of torque, because you have a quantity vertical and horizontal perpendicular to each other, and it just makes sense to me. You'll see the connection with that momentarily. So here we have plank or a rod that's pivoted. It's free to pivot from the pivot point, length r. We're going to apply force vertically upward. Now, the direction of this force, if we extend the line down here, basically what we have is the line of action. The line of action is a line that passes through the direction of force applied to some object. And so that's important. We can see where that intersects this line down here, and the extent from the pivot point to where that intersects is r sine of phi. So that's going to be our L. L is r sine of phi. Alternate interior angles, here's the direction of phi. So that's the difference, the angle between the force and the direction of the radius arm. So we'll really be calling this a radius or moment arm of the rotating system. So we can break the force into F tangent of, well, F tangential, which is F sine of phi, and then F radial, which is F cosine of phi. And only one of these contributes to the torque, and I'll give you a hint, it's not the radial part. Okay, that does not produce any rotational motion or rotational acceleration. So torque is actually then just LF. So it's the length of this to the intersection of the line of action times that force. Now notice that this is a smaller length than the radius arm itself, but it's the part that's perpendicular to the force. So we can also call that R times F tangential. So the product of L and F is the same as the product of R times the tangential part of the force. Those products are the same. So we have RF sine of phi. And that's what we call and is known as torque, which is R cross F. The unit being Newton meters. Well, yeah, that's right. Radius meters, force in newtons. Now, is that a joule? Newton meter is a joule, right? Well, no, that is certainly not a joule. Well, what's the difference? There's a significant difference in terms of how these physical quantities are applied. The newtons needs to be perpendicular to the meters. So when we're talking about a joule, we have the newtons and the meters parallel to each other. Now they're perpendicular to each other. So you got to be careful in general when you consider units, not just to look at the units, but the way in which the units are used, because you could be easily led to think that this is a joule, and it's certainly not. It's a cross product, not a dot product. The angular quantities that we deal with have a vector nature, so let's just get some definitions here. We have a disk that's spinning at omega. It's going in the direction shown, of course, like this. And it's easy to visualize that direction of omega, but it's got a vector direction as well. So what you do is grab that disk with your grubby right hand in the direction of your fingers, encircling it in the direction of the arrow, and your thumb will point to the direction of vector angular velocity, omega. Now, if that angular velocity is going up, then of course we have an angular acceleration. So if omega is increasing, then in that direction, once again, you put your fingers in the direction of the way in which the angular velocity is increasing. So it's accelerating this way as well. And then we have alpha, vector alpha, being in the same direction. So it's a right-hand rule thing. And the same thing, we have omega here as a vector, but if omega is going down, then the angular acceleration is like directed the opposite way. It's going this direction. So if you put your right hand around the disk, you will see that the angular acceleration is pointing the opposite way. So the rest just follows naturally. If omega is this way, we have vector omega. If it's going up, then the angular acceleration is in the same direction. If the angular velocity is going down, then the angular acceleration is the opposite way. So it's all the direction of the right-hand rule, and whether the acceleration is in that same direction or the opposite direction. So then this kind of puts it all together. We have a disk with vector position r, and applied to the edge of that disk, we have a vector force F. Now the torque is perpendicular to R and F. So be careful not to do vector addition mode here, but think of taking this force vector and putting it down here, and then crossing R into F with your right hand. And if you do that, your thumb points in the direction of the torque, R cross F. So it's like this. Very good stuff, huh? Let's move on. Let's now carefully consider the torque and angular acceleration for a rigid body. So we have a coordinate system here, and we consider a path. We put a particle of mass m on that path. So that's an ith particle of potential infinite number of infinitesimal particles. With the vector position r sub I vector, but the actual rotational radius is r sub I. So this radius is perpendicular to the axis of rotation, which is the y-axis in this case. Now this is the force applied to that particle. And it's not real obvious what direction that is, but it will be in a moment, because this is the tangential part, and this is the radial part. So now you can see it, can't you? Well, there's also a y part to this. So that force is in three-dimensional space. Now two of these, Fy and F radial, they don't contribute anything to the torque about the axis of rotation. The only thing that contributes to the torque is the tangential part. So those two other forces, Fy and F radial, they do not affect the angular acceleration. But F tangential is ma tangential. All right, and tangential acceleration, as we learned, is r alpha. So that shouldn't be a surprise. Let's multiply both sides by r. We get F tangential r is mr squared alpha. What's mr squared? For a point mass, we already learned that mr squared is the moment of inertia. So the moment of inertia is found from this starting point, recognizing that F tangential r is torque, and thus the torque of the ith particle, actually on the ith particle, is its moment of inertia times its angular acceleration. Now for a rigid body, you know that the angular acceleration is equal for all bodies, that all points or infinitesimal masses at different locations on that extended body. Thus, the sum of the torques is the sum of the miri squareds, quantity times alpha, and we have that this is the total moment of inertia. And thus we have the sum of the torques is I alpha analogous to sum of F is ma. And this expression is arguably the most fundamental and important in all of rotational dynamics. Now let's look at a few example problems in the next video.